All right, so we're going to be finding the area of our polar curves. So some of these polar curves are going to have regions that are enclosed, and we want to find the area within that region. So before we do that, we got to redo a little review of area of a sector. So we're going to be cutting these up into little tiny sectors. So if you look at our sector here, it is a portion of a circle. So all the way around is pi r squared. So that's for our entire circle. So now if we want just a little part of the sector, that little sector, that little portion, that little pi piece, then that means we are looking at a portion of it. So that would be theta over 2 pi, because all the way around is 2 pi times our pi r squared. And so if we do a quick simplify by canceling the pi, we get 1/2 theta r squared, or 1/2 r squared theta. And you'll see why we're writing it that way in a minute. Both are good formulas. So what happens, we have our curve here, 1 plus sine theta. And as we move around, our angle goes from 0 to 2 pi. It creates all of these little sectors, right? It's one way of looking at it, like this. So as our parameter theta goes all the way around, it goes from 0 to 2 pi, and it does this. It's creating all of these sectors. Let's look at that again. So as we go from 0 to 2 pi, we can create all of these sectors. And here's how. So if we use all of those sectors, it will give us our area. So if we look at one sector, it's not really a sector. So what we do is we create one that gives us kind of what we want right there, right? And we call that, see how it's hitting the graph itself here? That's our radius. And our radius is equal to 1 plus the sine theta. So that is our radius here. And its angle itself is d theta. So if you remember our integrals, we're going to go through this as a sum and everything, but it just becomes this area of our sector is 1/2 theta r squared. And our theta here is actually a d theta. So that is the angle of our sector. So if you go back here, you can see here we have theta, it's now d theta. And then we have 1/2 r squared as well. So that is our integral. So if we do the integral from start to finish of 1/2 r squared d theta, it will then add up all of these little sectors as we move through the graph. So as we go from 0, you can see I'm going to end at 2 pi, to 2 pi, our integral will then add up all of those sectors from 0 to 2 pi. So as our little dot moves around, right, that's giving us our thetas. Those thetas plugged into our formula will give us all of those areas, giving us the area inside. Okay, so now all we have to do is plug things in. So to get the full cardioid, we got to go from 0 all the way to 2 pi. So we're going to go from 0 to 2 pi. And then it's 1/2, and we plug in our r, which is 1 plus sine theta d theta. And now all we have to do is multiply all of that out. Okay, so we get 1/2, and then 1 plus 2 sine theta plus sine squared theta. And then we'll distribute the 1/2. You can also just take it out as well. So we get 1/2 plus sine theta plus 1/2 sine squared theta. And if you remember, when we do have a sine squared or a cosine squared, we're just going to make it into a cosine of 2 theta, a double angle. So we end up with 1/2 plus sine theta plus, and then now I'm going to put 1/4 because it's 1/2 cosine of 2 theta. So remember, it's going to be, sine squared is 1/2 of this, so 1/2 and a 1/2 is 1/4. So continue along. So again, we're going to plug this in our calculator, and it will verify everything is correct. So we're just trying to find the exact value, make sure it's correct. All right, so 1/4 and 1/2 makes 3/4 plus sine theta minus 1/4 cosine 2 theta. All right, now we're good. Everything is simplified, brought together. All right, So we end up with 3/4 theta plus cosine theta, and since it's a cosine, you make it a negative, minus, and then this is going to be, we're going to take out a 2, so 1/8 sine of 2 theta from 2 pi to 0, and then just double check it. Sine of 2 theta would be cosine 2 theta times 2, cancels with the 8 to make a 4. Everything looks good. So now we have 3/4 of 2 pi minus cosine of 2 pi minus 1/8 sine 2 times 2 pi. And then now minus 3/4 of 0 plus cosine of 0 plus 1/8 sine of 0. All right, so we end up with 3 pi over 2. And then cosine of 2 pi is 1. And then sine of 2 pi is 0. So that's gone. Don't need it. And then 0, 1. And then 0. So we have 0, 1, 0. So we end up with 3 pi over 2. All right, and now all that's left is to take our modern technology, we plug it in. So you want to plug in the original equation. So it's 0 to 2 pi. That gives us our full cardioid. And then it's 1/2 r squared d theta. So we just plug the r in as it was given to us. And it says 4.712. And that is the exact value for 3. And 3 pi over 2 is the exact value for that decimal. So it checks perfectly. So all you're doing on each of these problems, again, is making it into little sectors, which is 1/2 r squared, and then we know it's d theta, that's our thickness. So we're plugging in that formula, and our integral is adding all of them up from 0 to 2 pi. So if we know our interval to create one full cardioid or whatever curve that they want, then we know what our start and finish is. And all we have to do is plug in our r into this formula, and it'll spit out our area. It's pretty cool.